So the first person that we learned about was Einstein. And for the exam, you'd basically just have to know, what did Einstein do? What like theory or what experiment was related to the scientist? So Einstein, he basically discovered the photoelectric effect. And I got this off Wikipedia. It basically just means that he did this experiment that confirms how light energy is carried in discrete quantized energy packets to explain experimental data from the photoelectric effect. And this basically means that Einstein, he did an experiment where he applied energy to a metal surface, so right here. And then when he applied energy, this caused electrons to be emitted from the metal. And his experiment basically confirms that the equation E equals HV was correct. So joules equals Hertz or Planck's constant times frequency. This basically verified that, because every time you shine energy in the form of like light or something at an object, the electrons that get emitted is only on like a defined quantity. It's not going to be on like a spectrum. It's going to be basically confirming that staircase pattern that we learned from quantized energy.
All right, so the next one is Bohr's model. So I think his name was Niels Bohr. Niels Bohr main purpose study was studying hydrogen atoms. So based on his studies with hydrogen, he proposed that all atoms have electrons orbiting around their nucleus in quantized energy levels or shells. And this kind of relates back to the Rydberg equation, where E is equal to the Rydberg constant times the difference between 1 over n final squared, right?
Oh, well, this one, they put initial first and then final last. But in lecture, I think we learned it the other way. So yeah, there was like a negative sign in front. And let me just make some annotations really quickly.
Yeah.
So lecture,
you distributed the negative. The negative got distributed.
It was negative RH times 1 over n final squared minus 1 over n initial squared. Yeah, I wasn't paying attention when I found this equation online, so I didn't notice that there was no negative sign here. But these are basically the same thing. I would just stick to what you learned in lecture.
Yeah.
Because when you move on to like physics 2A or physics 2B or whatever.
Or 50 and 51.
Yeah, when you calculate change in something, it's always going to be final minus initial.
Initial, yeah.
So I would just keep to that. Whoops, sorry about that. Okay,
it's
go ahead and continue.
Yeah. So yeah, but that's pretty much Bohr's model dealing with hydrogen. Oh, and where's the next slide? Next slide.
Okay. Oh my God.
So Bohr's model continue.
So basically, Bohr's model, it basically confirms that the Rydberg equation will only work for hydrogen, though. There are limitations to this because, one, it only works for hydrogen because that was the only atom that Bohr worked with. And this basically confirms the emission line spectrum for hydrogen. So if you remember in lab, this is what you all did, right? Oops. So in lab, you looked at the emission spectrum for hydrogen, and notice how the colors that you saw for hydrogen, which was only either going to be red, blue, or purple, they match the hydrogen emission spectrum, like pretty much very exactly. So n equals 4, n equals 3, n equals 2, and n equals 1. And this is because every time you shine like a light or an energy at a hydrogen atom, it can only be emitted light at these frequencies.
Yeah.
Meaning, so this basically means that every time hydrogen emits energy, it's going to be quantized. It's going to be either this one, this one, this one, or this one. There's no spectrum. Okay.
And I believe in Dr. E's class, she did say about like 4 specific wavelengths, and I think those are the 4, right?
Yes, so these colors will correlate to a specific wavelength. I think red is like around
I think it was like
700
yeah,
something
700.
nanometers.
Yeah,
And purple is like
400.
around
I think it was like 400.
400 nanometers or so.
Yeah.
But we're just estimating, but again, these will all relate to the Rydberg equation.
Mhm.
So you can calculate this exact energy by using the negative or the RH times final squared minus 1 initial
Over squared.
squared. Yeah.
Yeah.
Alrighty, so let's move on to the next topic.
Oh, all right. So the next one is de Broglie. So what de Broglie proved, he proved that electrons also have a wavelength on a particle, which made the equation of lambda is equal to h divided by the mass times the velocity. And of course, wavelength is calculated in meters, velocity is meters per second, and then the mass is in kilograms. But this also related to the matter waves theory, where moving objects such as electrons can behave like a wave. So in lecture, I remember that Dr. E went over like specific waves. Same concept. Electrons behave in certain wave patterns based off of the frequency and the wavelength. So the wave particle duality is where waves could behave as particles, so like photons of light. And same thing can happen with electrons. I believe that's electrons. Well, electrons and particles will have the same sort of behavior with wavelength and frequency.
Yeah, basically this de Broglie, he basically correlated all those equations that we've learned in lecture. So like the light one, the frequency one, everything, and he just made it into one compact equation. And he basically related the theory that light can behave like a wave and a particle. And he basically related that to electrons, so matter. Basically, because light can behave like a wave or a particle, so can matter. So an electron can also behave like a wave. And this equation will prove that.
The next slide, because I can't press next. So the next one is Heisenberg's uncertainty principle. So there's three sort of keynotes for Heisenberg. So in classic physics, you know an object's momentum and position at all times. In the more recent new physics, you only know an object's momentum or position, not both at the same time. This allows us to describe the location of an electron as a probability. So remember in lecture when Dr. E sort of talked about an electron like moving everywhere, but not really a precise location. So it's kind of like, how do I say this? How would you describe this? It's like an electron is an always moving object. So we don't know where it's going to be at precisely, but we know where it could be at. So think of your entire day. So think of your entire day, what you did today. If someone were to ask you, they wanted to meet up with you at a certain location based off your trail, they can figure out where you were and find a probable location where you will be next based off of your travel. Same thing with an electron. So we can't really precisely locate the location of the electron, but we can assume a general area where it could be. That's why it's like the whole electron cloud thing kind of relates with it.
Yes, so basically Heisenberg basically proved Bohr's model wrong. So I'm gonna like draw an X over that. Because Bohr was like, oh yeah, we can know where an electron's location will be as long as you know like the n energy level. So like for hydrogen, it was n equals 1, n equals 2, etc. But this apparently does not work for all atoms. This only works for the hydrogen atom, which is what Bohr based all of his work on. So this is why Heisenberg's theory was very important, because Michael brought up the electron cloud. And if you remember Bohr's model, probably from like high school or whatever, he drew his electrons in like little shells, right? So he was like, as long as you know the energy level, you can know like where the electron will be. but this is wrong, right? This only works for hydrogen because of that emission line spectrum. So Heisenberg was like, okay, here's like a better model. Basically, electrons are always going to be in a cloud. So it can be at like any of these like endpoints. Because electrons, they move very, very quickly at the speed of, or they move very, very, very quickly. So we cannot know for sure where an electron will be, but we do know that this cloud region is like a better estimate of the location of electron. This is why he calls it as a probability and not like an exact location.
It's Schrodinger, that guy, yeah. Pioneer theory of quantum mechanics helps us find the probability of an electron's location. So basically prove Bohr wrong. No, not Bohr. Wait, sorry. Heisenberg proved Bohr wrong. Schrodinger based off his theory off of Heisenberg. So using quantum mechanics and quantum numbers, we can find a general probability area of where an electron can be located or not, since the electron moves very quickly and at random. Does that kind of help? Plus or minus here and there? All right, so next slide. Speaking of quantum mechanics, quantum numbers. So the whole point of quantum numbers, they allow us to, they will help us tell the, address of an electron. So it's kind of like the social security number that y'all have, or your home address, or I don't know, phone number. That's what quantum numbers are. So your quantum numbers consist of 4 specific values: your N, your L, your ML, and your MS. And here they are.
Okay, so this looks like a lot, but basically this slide is to just go over each quantum number in detail. So N is called the principal quantum number, and it basically tells you what energy level or shell that an electron could potentially be located. The larger the N is equivalent to a larger sized atom, and a larger N also means that the electron is farther away from the nucleus and thus will have higher energy. So if you remember from, from hydrogen, I think hydrogen only has like 4 energy levels, right? And that's because hydrogen is very small. But something larger, like, I don't know, phosphorus or bromine, they can have energy levels that go way higher than 4. And this makes sense because bromine is a larger atom. So if you were to draw like hydrogen versus bromine, for example, hydrogen would look like this, whereas like bromine would look much, much larger. So we can have a lot more of those circles, whereas hydrogen will only have like 1, 2, 3, 4, something like that.
Mm-hmm.
Okay. And then the next one is called L. L is the azimuthal quantum number, and this tells you the orbital or the shape of the atom. So there are 4 types of orbitals, S, P, D, and F, and we use the numbers 0, 1, 2, and 3 to represent these 4 different orbitals. The next one is the M sub L quantum number, and this is the magnetic quantum number. And this basically tells you the orientation of the orbital. So for example, S orbitals can have only 1 orientation. So therefore the ML for S orbitals will always be 0. P orbitals can have 3 different orientations. So therefore it can be -1, 0, or +1. And this basically correlates with, so I think in lecture, Dr. E drew something like this. So S orbitals are always going to be like this circular shape, but then P orbitals, they're going to be like a dumbbell shape, so something like this. So this is S, and this is P orbitals. So the orientation of P orbitals basically refers to how is it like oriented in space. So P orbitals can have 3 different orientations. It can be like up and down like this, or it can be like kind of diagonally like this, or it can be diagonally to the left like this. So this would be like -1 orientation, this one would be 0, and this one would be +1 orientation. So these three numbers are basically the ML quantum numbers, because it will tell you, oh, if I have a p orbital and my ML is 0, it means that my electron will be in an orientation like this. Okay, so that's why we have ML quantum numbers. They tell you the shape, or L will tell you the shape, and then the ML will tell you how that shape is oriented in space. So like straight, or like diagonal, or like diagonal to the right. Okay, and then lastly, we have the MS, which is the spin quantum number. And this tells you the direction up and down, up or down, of the angular momentum of an electron. And to determine the MS number, you must look at the last electron placed to determine the spin, and actually to determine all these quantum numbers too.
Mm-hmm.
Okay, so that was a lot. Let's talk about paramagnetic versus diamagnetic. So diamagnetic basically refers to having no unpaired electrons in a quantum number configuration. So if you look here, these arrows represent our electrons. And basically every single electron has a partner. So this will mean it's diamagnetic. And diamagnetic quantum numbers, or diamagnetic elements, will not interact very much with a magnetic field. On the other hand, we have paramagnetic, and this means that there will be at least one unpaired electron in the quantum numbers for that element. And this means that that element will interact much more strongly with a magnetic field. And this kind of makes sense, right? Because if you look here, everyone has a partner, so they're really happy. There's no need to like interact with an external magnetic field. But here, everyone has a partner except for at least one. So this one electron will be much more likely to interact with like an external force, because it wants like a partner. It wants another like object with it so that it can be a little more stable.
Yep. So here are the, well, how do I say this? How do I say this? The S, P, D, and F of your quantum numbers. So to the left in the blue, that's your S block. The one in the green is your P block. The one in right is your D block, and the one in purple is your F block. So the numbers on the side just tells you the principal quantum number, which is the value of n, and then you can figure out how to find the other three based off that n. So like the first row is 1s, then 2s, then 3s, 4s, and then 3d, 2p, 3d, 4f. So yeah, our advice, we would say that probably like on your for like side notes, like label out your periodic table like this, so that way you're able to figure out which set of quantum numbers would match up to the test. Because I know like a good test question would be, what is the quantum number of this element? So you have to find out the element, but you need to know what the number is. So knowing this orientation of it on your periodic table will be helpful. Oxidation states. So they're kind of like the oxidation numbers, but you're dealing with the metals and non-metals. So metals can only have positive charge oxidation states, while non-metals can have either negative or positive. So you would have to look at the electron configuration for that. So, what was the one in argon? I'm gonna explain this as best I can. So sodium, the electron configuration for it would be, why are you doing this to me? I don't have my periodic table on me right now. One second. Sodium, there we go. So it would be bracket N, E, and then 3, it's a 3, S, not supposed to be a 2, 3s1. So you always look at, you don't look at the noble gas, you would look at this. So whatever the after electron configuration, that's what you look for oxidation states. So oxidation states is kind of like losing or gaining electrons. So kind of has to relate to like why some elements, when they turn to ions, they have positive or negative charge. Same thing. So it's just the whole of them just like, what is the probability of them losing electrons and stuff like that. So for sodium, Ne, which is the neon, it already has all the shells filled, but this 3s1, if sodium were to lose this electron, so this goes away, it will end up having a +1 oxidation state. Now, do note that only metals can have positive charge oxidation states. So this would be the final answer for sodium only, because it is a metal. So, however, for bromine, it would be, I have to look at this again. Oh, it's so long. Forgot about that. The krypton, argon. Argon. 4s2, no, 5s2, 4s2. 4s2, 3d10, and then 4p5. So bromine can have either positive or negative oxidation states. So in order for bromine to be like, let's see, the nearest noble gas, which is krypton in a sense, it'll need one more electron. So so if it gains one more electron, so if you add one electron to this, it will become 4p6, right? So bromine will have an oxidation state of -1. So it's one of the oxidation states that it could have. However, oh, whoops, I need that 5. However, it can also lose electrons. So first it would lose, wait, it was -1 + 5 + 7. First, it would lose the nearest, it would lose the most outermost shell. So the first one it would lose would be the P or the S first? Claire?
P.
P. It will lose the P first. So all these electrons will be lost. So another oxidation state number that Br can be is a +5. Because it lost those 5 electrons. Now, if it can go even further, it can also lose the 2 electrons in the 4s2. So electrons will always be lost in the highest end level. So you would work your way back until like you get like until like all the electrons would be assumingly gone. So the last oxygen state that bromine can have is a +7, since it lost those 2 electrons. So -1 from gaining 1 electron, +5 for losing the 4p5, and then +7 for losing the 4s2 and the 4p5. It doesn't lose the 3d10 because the 3d10 would be the most stable electron orbital diagram out of the 3. Since there is so much more room to play with the 3D level than that of the P, and since there's more room to deal with in the D orbital than the P and the S orbital. The P and the S orbital are like smaller compared to that of the D orbital, which is the reason why when you do your Lewis dot structures, elements that are in the row 3 and below can actually have more than 8 electrons surrounding them. That's where this oxidation state kind of relates with them. So knowing about Lewis dot structures, the next topic would be the Lewis dot structures. So these are the main rules to know about the Lewis dot structures. So we got to look at the rules. Got the Cosmo over here. So the rules are: count the number of 12 valence electrons, determine the arrangement of the atoms, draw a bond between the central atom with the surrounding atoms, subtract the number of electrons used to make the bonds from the total, place the remaining electrons on the surrounding atoms, that still needs an octet. If there are any electrons left over, add them to the central atom, and then check the center atom if it has an octet. Remember that atoms on row 3 and below do not need to follow the octet rule. So anything after, I think it was neon, anything after neon, you can technically speaking have more electrons in there. But this is more for like the non-metal areas. So non-metals, roller structures. Mainly, most of the time is non-metals. So that's the reason why that like when you do your Lewis-Dot structures, they didn't have that many of the metals, because that would be more ionic. So for covalent bonds, such as Lewis-Dot covalent bonds, which is a non-metal, that's how they kind of correlate. So here's your periodic table. We only need to so anywhere from here down, do not need to follow octets. That's so atrociously written. So all of these elements from sodium down, they all do not need to follow the octet. However, do not need to follow the octet. But however, for like carbon, neon, oxygen, and fluorine, they have to follow the octet. That's the 4 you have to be careful of. But with like phosphorus, sulfur, and chlorine, they don't necessarily need to follow the octet. So why don't we try out problem? So what is the Lewis-Dot structure of CH4?
Let's see. So the first step is to calculate the number of valence electrons, right?
Yeah.
So carbon will have 4 valence electrons, plus hydrogen has only 1 valence electron.
Yes.
But there are 4 of them. So we gotta do some mental math. We have 8 valence electrons total.
I don't like math.
So I don't either. But now that we have our 8 valence electrons, we're going to start by putting the least electronegative atom in the center. So in this case, it would be hydrogen, but I think the rule is the least electronegative atom goes in the center except for hydrogen. So it's going to be C. And now we're going to draw the rest of our atoms around the central atom. Does not matter where you put them.
Yeah.
And now we're going to draw bonds connecting these atoms to the center atom. So now we have to do some more math. For each bond that we put down, that's going to be how many electrons?
2 each.
2 electrons each. So let's count how many we placed down so far. 1, 2, 3, 4, 5, 6, 7, 8. So 8 minus 8 gives us 0 valence electrons left. And when we have 0 valence electrons left to distribute, it means we are done.
Yep.
So this would be the Lewis-Dot structure for CH4, which is methane.
Yeah. A quick side note. For lecture, you can just only draw the bonds, but I know in the quiz, when I took the quiz for Lewis-Dot structures, it would have to be, oh, thank you. You'll have to actually show the dots for each of them. Yeah. So only in the lab quiz, you have to show the dots for the Lewis-Dot structures. In lecture, we don't give 2 S words. You just, because multiple choice, so you can just like, oh yeah, it's that one. Yeah, totally. But that's only for lab where you actually have to show all the electrons. Yeah. So yeah. The next one. Actually, it's like 20 minutes left.
Yeah, we're kind of running low on time. So,
all right. So the next 2 are like for your own benefit and practice. So the PCl5, that's a good one to work on. The Xenon F4, I remember that this one was on my quiz for lab. So if you can do the Lewis-Dot structure for this one, you should be in good shape. And I know PCl5 was also another popular one that is used in lab and lecture. So
Yeah.
Yeah.
Oh, another important thing to add, I don't know if you will ever see this in lab or lecture, but suppose you have like, whoops, I need to annotate. Suppose you have like um, xenon F4 with like -2, something like that. Yeah, so I don't know if you'll ever see this, but don't forget that the charge is really important in the structure, right? So when you calculate the valence electrons, it's going to be whatever valence electrons you calculate plus an
The
extra
charge.
2.
Yeah.
Yeah.
So before, all of them that we've been dealing with had nothing in the charge, but if you actually have if you have a charge right here, then you would have to put, like Claire said, you would have to put that in your calculations.
Yeah,
If
and then
it's
similarly, if it's like xenon F4 +1, for example, the valence electrons will be whatever the valence electrons are calculated minus 1 extra electron.
because because the electrons are negative.
Yes,
So if you lose one, you're becoming more positive. So that's
exactly. So don't forget the positive or negative charges. They will affect the Lewis dot structure when you draw them out and you calculate them. You're going to be like, why do I have like an odd number left over? Like, what do I do with it? So yeah, please double check the charge for these valence electrons. And it's going to mess up your Lewis structure if you don't.
all right. So VSEPR geometry. So valence shell electron pair repulsion geometry. You don't need to know the exact definition of it, but I'm just gonna write it down right here, or the exact abbreviation of it. Oh, no, we're not supposed to show that yet. But I'm just gonna write it down here. So valence electron. Oh, valence shell. I can't spell. Shell electron pair repulsion. This might be a random question that Dr. Esfandiari could throw out with y'all. So hint, hint. Just like, I don't know, random extra credit question. What does VSEPR mean?
Wait,
Oh,
really?
valence shell electron pair repulsion. I remember when I took Dr. Kelly's class, I had to know the definition, and that was worth a 5-point question. But yeah. But yeah, so valence shell electron pair repulsion. So the Vespierre geometry. The Vespierre makes life easy. So right here are just the Claire. Right here are just like the list of the polars and nonpolars of the geometry. So your polars are your bent, your square pyramidal, your seesaw, and your pyramidal. And your nonpolars are your linear, trigonal planar, tetrahedral, octahedral, square planar, and T-shape. For a polar to happen, you need to have an unbalanced share of electrons. And for nonpolar, all electrons are distributed evenly. So even if like you have a molecule like example HF, whoops. So like HF, even though this is a linear shape, it's polar because of these lone pairs that fluorine has. So be sure to draw out the geometry of it, because sometimes if it's a linear, be sure to double check the surrounding atoms if they have any electrons around them. So even though this is a linear structure, it's considered polar because fluorine has these lone pairs attached to it. So yes. So, and here's the chart. Aliens. So yeah, kind of all look like little aliens and stuff. And I said before, your bed, your pyramidal, your seesaw. I believe these are the ones that should be the polars. So your bent, your pyramidal, your seesaw, this other bent over here, and your square pyramidal. These should all be the polar molecules. So they're polar, like the polar bears. So all these would be the polar, and then everything else would be non-polar. But always be sure to draw out the geometry, or the Lewis dot structure. Sorry, draw out the Lewis dot structure. And yes. So next slide. Polarity is, well, I stated before, if a molecule has an unbalanced placement of electrons, then the molecule is polar. However, if a molecule has a balanced placement of electrons, then the molecule would be nonpolar. So pretty straightforward with the electron. So it's pretty straightforward concept. So this is for your own benefit and practice, because I think we're running out of time. Yeah, we're kind of running out of time. So try these out on your own. Try these out on your own time for practice for polarity. It's a little polar bears. And this would be the answer to it.